We look at a house and usually just see the shingles. It looks like a simple, solid lid resting on top of a building. But beneath that exterior is a highly interdependent structural framework. This hidden system is built from distinct specialized parts called roof members. Every piece has a strict, non-redundant job. Their first engineering requirement is straightforward but demanding. They have to physically support the immense weight of the roofing materials, the wood, the metal, or the tiles. Their second requirement is to take all of that suspended weight and channel it safely down into the foundation walls. This poses a physical problem. Thousands of pounds of material are hovering over empty space. Without the right geometric arrangement, gravity would pull the entire structure inward. To see exactly how this works, we are going to build a roof frame from scratch, piece by piece. We'll look at the 6 vital structural components that make this possible. Understanding a roof means mapping a system of load paths, tracing exactly how forces travel from the very peak of the house all the way to the ground. We start with bare load-bearing walls. First, we add plates, horizontal wood placed flat along the top to spread weight evenly. Next, the ridge, a single horizontal beam suspended high in the center. The ridge acts as the top connection point. It dictates the highest line of the roof and anchors the top of the angled framework. Between the top ridge and the bottom plates, we have established the boundary points. Every ounce of weight must be successfully transferred from the top down to the base. To bridge the gap, we use rafters, sloping beams of wood or metal. As the primary bones, their angle catches gravity, channeling weight directly down into the wall plates. In standard designs, we rely heavily on common rafters. A common rafter runs continuously from the top ridge down to the wall plate. As the architectural shape changes to a hip roof, the framing adapts with hip rafters. Hip rafters run specifically along the outside corners of the roof, providing the angled spine needed for those intersecting planes. To fill in the gaps created by those diagonal corners, we use jack rafters. Jack rafters are deliberately cut short, connecting directly to the side of the hip rafters. Whether common, hip, or short jack segments, all rafters execute the same physical purpose, forming the structural incline carrying weight toward the foundation. But this sloping geometry creates a severe secondary problem. Massive downward weight on an angled surface deflects sideways. The bottom ends of the rafters physically want to slide apart, kicking the supporting walls outward. Left unchecked, the walls would bow and collapse. To solve this, builders install ties. Ties are horizontal pieces that physically bridge the gap between opposing rafters. By resisting the outward spread, ties pull the framework inward, directly countering the outward thrust. Structural stability requires the roof to support downward weight while simultaneously neutralizing its own internal outward tension. With the internal skeleton stabilized against gravity and tension, the frame needs secondary supports to hold the actual exterior shell. We add purlins. These are horizontal supports placed squarely across the middle section of the sloping rafters. Rafters covering long distances can sag under heavy loads. Purlins intersect them halfway down, adding extra midspan support, specifically designed to bear the weight. Finally, we apply the outermost framing layer, laths. These are thin strips of wood or metal fastened horizontally across the exterior face of the rafters and purlins. They create a tight grid, acting as a fastening surface to securely lock final exterior layers, like individual roof tiles, directly into the frame. Purlins and laths act as connective tissue. They bridge the gap between the heavy load-bearing skeleton and the external covering that shields the house. If we look at the fully assembled roof frame, the engineering directly mirrors biological anatomy. The rafters act as the primary bones, or the rib cage, providing the macro shape and carrying the bulk of the physical stress. Down below, the plates function as the base of the body, absorbing the weight from the ribs and planting it firmly into the legs of the foundation. At the very top, the central ridge acts as the spine, connecting the ribs at the apex. The ties do the work of internal ligaments and muscles, constantly pulling inward to hold the skeleton together against outward physical forces. The purlins wrap around the ribs like bands of extra support muscle, and the laths form the subcutaneous layer, creating the precise surface area required to hold the exterior skin in place. None of these parts can do the entire job alone. Every specialized member is entirely dependent on the others to function as a unified, load-bearing system. This document outlines a simple memory tip to permanently lock in the 6 specific parts we just built, the RPRT-PL acronym. We have the core structural trio, rafters bridging the gap, plates anchoring the bottom, and the ridge tying the top. Then we have the secondary supports, ties to stop the spread, purlins to brace the middle, and laths to catch the exterior tiles. We started with a physical problem, suspending thousands of pounds of material over an empty room without the structure caving in. The roof achieves this by systematically passing the baton. The weight of the exterior covering pushes into the laths, down into the purlins, through the rafters, and finally distributes evenly across the plates and into the foundation walls. Mastering these parts allows us to map the routing of physical force. This precise management of gravity and tension is what keeps a roof strong, stable, and safe above our heads.